more local roads. Okay, so with that, you can see that we have the location of the bridges. We break down the bridges into steel and concrete bridges, and the idea is that there would be having different vulnerabilities in flooding events. We also have the distribution, spatial distribution of the traffic. You can see some parts of the state or the district are pretty, have high traffic. Accordingly, they have also higher capacity as well. So all of these are integrated into the modeling scheme that we have. So with that, I would like to first start with introducing a general resilience framework that I normally use and kind of is implemented in such a way that can be applied in different contexts and different hazards. I actually call it a multi-hazard resilience assessment framework, which basically is consisting of a hazard characterization basically component, which looks into the hazard, the type of the hazard, frequency or intensity measures that are associated with that hazard. It has an exposure identification where we understand what is the likelihood of different assets or components of our infrastructure system that can be exposed, and what are the attributing factors for that exposure. We have asset vulnerability measures that there are different ways that one can measure the vulnerability. One of the more famous ones are the fragility functions. And from there, we can set up a resilience assessment, which basically covers two components. One is the risk assessment component, which basically we would like to understand the impact of an individual asset on the performance of the infrastructure system in terms of both direct damages and also potential cascade effects. Then the more important part, which defines resilience, is really the recovery part, where not only we are interested in the immediate aftermath of the event, but we are also looking into the temporal evolution of the various performance measures that we consider for the system and how they evolve as we are trying to recover from the system. And then all of this kind of forms a computational backbone that kind of establishes this framework. And then at the end of the day, what we really want to do with this computational backbone is to be able to do decision making, to make decisions. These decisions are either pre-event decisions in terms of mitigation or post-event for recovery, or a combination of both. They can be short or long-term decisions. Short-term decisions can be things such as emergency response or deploying your maintenance crew and such, or medium ones are things such as repairing and the damages, and the long-term planning is more of a, how to make this more resilient for future events. And the hope is that this decision-making finally is going to impact your exposure conditions, for example, with creation of, in the case of flooding event, creation of catch basins. You're preventing the flooding to happen to some of your assets, or you might, for example, create some mitigation for some of the assets that may result in enhancing their kind of or reducing their vulnerability to that extreme event. And of course, you may end up doing some sort of planning for future events that will help with the recovery in the face of future events. So that's kind of the general framework we're going to work with. So moving forward from this one, let's look into this context that we're looking for the characterization of the hazards. Here, what we have in mind is basically what we have is the 5 different basins that could result in flooding. We also have different return periods or basically probability of occurrence of these events. The basically intensity measure of interest in this case of flooding flood events, what we are looking for is flood water depth, and also in a sense the boundary of flooding events. So this is something that was given to us by our the State of Iowa Flood Center located in University of Iowa. The hydrologists had conducted the scenarios there, and we were given about more than 800 scenarios to work with. So that's basically our hazard characterization that we're gonna work with. The next item is the exposure identification. Basically, we need to have an understanding of the exposure of these different components. This not only requires our geographic location of these assets, but also an understanding of the features of these assets that make them vulnerable to this hazard of this target hazard, which in this case is flooding. And so we have the locations, we have a location of the roadways, we have the topography of this state as to what is the elevation of different assets. We also had access to all the plans, the design era, condition state of the assets, and so on and so forth. So that was kind of a, I would say in a sense, a lucky situation that we had the luxury of this type of data. There's a chance that in some of the infrastructure systems that are more proprietary in nature, such as electric grid lines is another area that I work on, such asset information is not available. In those cases, obviously, other types of approaches, such as use of proxy indicators, surveys, aerial imagery, and stuff like that can be used. But in this case, since we had the elevation of the assets, as can be shown here, we also had communications with the state engineers as to, what are the conditions for closure of different assets. And based on that, we defined exposure thresholds for these components of infrastructure. After that, we would like to measure the vulnerability of the assets. For this one, we actually conducted an extensive review of the different type of damages that had occurred because of historical flood events in the state. We were able to review more than 1,000 detailed damage reports on infrastructure that were damaged. Mostly, there were about 95% of them about either roadways or bridges. We were able to categorize the type of damages that are seen in these type of assets. And from there, we were able to also characterize the likelihood of the damage given the intensity measure, which is the flooding stage in this case, and develop empirical fragility functions. This is a very recent work that is coming out in bridge engineering. At the time that we were conducting this network analysis, we had not developed the fragility functions yet. So we considered something called the bridge performance indicator, which is basically a combination of the condition state of the bridge, which would be representing the vulnerability of the bridge to the flood event, and has in it a number of different things, such as the importance of the bridge and also the age of the bridge. So we use that for the vulnerability measure of a target that we used in our bridges. We also, from the data that we had, we understood that from the damages, the previous or historical damages, we noted that there are 33 bridges that are very likely to be damaged in hazards in these flood events. And we were able to measure, these are the IDs or identification numbers of these bridges in our program. And their locations are the 33 bridges are shown, and they're spread out different states, different parts of the district. And also we can measure what is the water level for different return periods or probabilities of occurrence of the flooding events. The color coded cells here also show that which river basin or flooding in which river basin would be the cause of that damage. So with that information, we would like now to go and kind of do the first stage of our resilience assessment, which is basically assessment of the risk because of these flooding events. For that, what we have is obviously the information for our hazards, the information for our assets and their exposure, and then we conducted flood simulations, and based on that, we could measure, different things such as what would be damaged, what would be closed, what would be the loss of connectivity, what is the traffic delay associated with those closures, what are the losses of opportunity because of those closures, and so on and so forth. And each one of them, what you can see is one performance measure for the network. And reality is that if you one looks into the literature of resilience assessment or enhancement, there's no concurrence on as to which the performance measure is the best performance measure. And in fact, in our study, we saw that necessarily, all of them do not point into the same conclusion. So it may be that one case that one bridge has a really high direct damage cost because of the type of the bridge that is there. But if one calculates the indirect costs associated with that bridge, they're not that much compared to another one. So one of the things that we did in our risk assessment, we kind of proposed a multi-scale risk index, which is kind of showed in this radial chart. And the idea is that we calculate, assuming that the bridge, the network is in its intact condition, would be the blue lines, and one can calculate the area under there. And then when the network is damaged, these different performance measures are going to decrease or kind of deteriorate because of that extreme event that happened. And then one can calculate the area under the red chart, and that would be some sort of an indicator of severity of the event or the criticality of the infrastructure assets versus those events. And that was one study that we conducted to provide a more holistic understanding of risk assessment and the performance measures that need to be accounted for when one does risk assessment. Another thing that we did with this framework was to develop risk curves. These risk curves are a very useful tool, especially for the decision makers to understand what type of risk they are willing to take and what that means in terms of a kind of annual exceedance probability and the associated cost with that in different scenarios of kind of extreme flooding events happening in different basins. And one can set this up in different contexts. We did it for direct costs and also total cost, which was a combination of direct and total cost, but other kind of performance measures can be calculated depending on what the decision maker wants in terms of a performance measure to make decisions on. Now, another aspect, as I mentioned, which is very important, is in the notion of resilience, we are not interested in the immediate aftermath of the event, but also looking at that temporal evolution of this metric that we are interested in. As I mentioned, that metric can vary, but one can kind of follow that metric and see what kind of evolution is happening during the time after the extreme event. And this is obviously not a trivial task to model at all. There are aspects such as, the limited data that we have on restoration tasks, specifically the complexities that we have with the emergency nature of the kind of restoration and recovery and repair, impact of, accessibility and resource scarcity that can kind of impede the recovery actions. We have addressed this in different ways. We have conducted a historical event restoration, kind of a study on the historical event restoration data through those more than 1,000 detailed damage record data that I mentioned. So we were able to find out for different types of damages that were likely to happen, what kind of activities are taken, normally how much they cost, and then we surveyed the infrastructure owners and also the contractors that were responsible for these recovery and repair actions to see how long they took to complete. We also use methods such as critical path methods to kind of model that cost and time and so on and so forth. With all this information, one can have a better understanding of, how to model that recovery and what are the constraints that one needs to put into that recovery model. Having all of that put together, as I mentioned, an important part now is that now that we can model all these aspects as close as we can with close to reality kind of assumptions, how are we going to go about and make decisions based on these parameters? So if we look into the famous resilience curve where we have the system functionality versus time, we normally have a shock event or an extreme event, which results in deterioration of that system functionality, however that we define it. And then after that, it may take us some time depending on how much plans we have, how much access we have to the damage assets, and so on and so forth. We start the recovery process. That is going to take some time, and hopefully we're going to get to what we were in terms of the system functionality before the event, or even into better conditions. Now, one of the aspects is that one can prepare for such event. One can prepare for such event by enhancing the characteristics of the assets that could be vulnerable to that event in such a way that they're in a better state. And as such, when that event happens in future, their loss in functionality will be lower. But at the same time, if we have plans in place which allows us to have a faster repair, for example, contracts in place, or just simply using more accelerated techniques, we're going to have a faster recovery. If our plans are very well laid out, we hopefully are going to get to even better conditions after the event and use that as a window of opportunity in a sense. Now, there are some issues with that kind of a decision making. It's a very complex phenomena, and a large part of it is that we have a huge uncertainty right at the first stage when we are making a decision as to what we need to mitigate. What are the assets that we need to mitigate? We don't have, and the reason for that is that we have no knowledge of what event is going to happen. That's completely uncertain to us. And the second part of it is that whatever decision that we make as to what to mitigate is going to impact how the system is going to perform after such event happens, or another event happens, or another kind of scenario. So in a sense, there's some sort of a loop in this decision making. What you mitigate is going to impact how your system performs, and as such, the best mitigation strategy may not be as obvious at the beginning because that secondary effects and kind of post-event response needs to be accounted for. And obviously, again, when a specific event happens, so the scenario is clear and you're looking into your second stage, there are many paths as to what to repair and what to recover and which one to do first so that we have a faster recovery. And that's, again, another problem that needs to be accounted for. So inherently, this is a nonlinear model if we wanted to do some sort of an optimization on it. So what we have done in this study is we have developed a two-stage stochastic programming method, or nonlinear two-stage programming method that basically handles nonlinear problems. It handles the interaction that is existent and is natural to do the two stages that we have before and after event. It captures the time evolution of the system operation after the event and deals with the uncertain parameters and finds the solutions. It has two stages, first stage and second stage. And the first stage basically represents, for example, in this case, bridge mitigation to increase the network capacity. And the second stage is the set of post-event recovery actions at different flooding scenarios. So With that, let's take a quick look into, I would say, boiled down simplistic view of what this two-stage stochastic programming is. The first stage includes basically the objective is to minimize, the general objective of this formulation is to minimize the costs and consequences associated with mitigating and also responding to disruption of the network. So again, that notion of first and second stage is really there. The first stage is about, what you're going to mitigate, what is the cost with that. It's understanding that when you're mitigating something or doing some sort of a construction on a bridge to improve its features against flood, there's going to be some traffic delay associated with that. But then also understanding the fact that whatever mitigation you do, obviously you're not going to be 100% perfect. You're not going to implement the a mitigation on every single asset that needs mitigation. As such, there's going to be some sort of an expected exposed cost, which is coming from the second stage. And again, this second stage, the idea is that there's some costs associated with this recovery of the assets. There's some traffic delay costs and also the opportunity costs associated with that. And so this is basically the NTSSP formulation we have. Again, there's some constraints to this, just again, boiling it down in a more easier way. Reality is that we do not have all the budget to mitigate and every single structure before the event. Some part of it is because of our restrained resources, but also because of the uncertainty associated with the event. So there's a mitigation budget that needs to be assigned. Basically, we consider the actual state of the bridge with that BP or Bridge Performance Index. Whatever bridge that has a lower than 70% BPI is going to be eligible for mitigation. Doesn't mean it's going to be mitigated, but it's eligible. We can use either conventional construction or accelerated bridge construction, which is a faster, more expensive approach. And during the mitigation, because it's not emergent conditions, we're going to have partial closure. So we're going to allow traffic to follow, but there might be some traffic. And again, bridge performance is going to improve step by step every 30 days. In the second stage, there's no limitation on the budget. The idea is that whatever that gets damaged is going to be fixed. And then obviously the bridge damage is associated with the assumptions we had or correlated with the flood depth. So the more the flood depth, the more likely the bridge is going to be damaged. Whatever bridge performance index after flooding that is lower than 50% should be recovered or repaired. Again, you can use either conventional or accelerated bridge construction. The assumption is that because of the damage and because of the existence of the flooding, for the first 1/3 of the recovery time, this asset is going to be closed, so there's not going to be any traffic on it, but then it's going to be gradually opened for the remainder of the 2/3 of the time of the project. So with that information, we have kind of set up the framework for that NTSSP. Now, the question is that how are we gonna go and solve this? It's a very hard problem. It's impractical to find a solution method with an accurate optimum to fit all of the problems we have. What are the problems? We have an NP, a nonlinear convex traffic assignment problem, which needs to be cyclically kind of checked to kind of represent that evolution of time that we were talking about. There's a mixed integer construction resource allocation problem also hidden in it at the middle level, which requires a lot of computational time. And then on top of all of it, it's a stochastic problem, programming problem, because there's a lot of uncertainty with your flooding. And on top of all of these complexities, we have our application environment is a real network, real world, large scale transportation network. So what we have adopted here is an evolution strategy. Basically, the idea is that the population of random resource allocation strategies compete in cost. That leads to a survival selection. And then the smaller cost is the better. And then the better strategies are chosen to produce next round candidate strategies and compete again. And after a few rounds, there's a possibility of creating a solution that fits the minimum cost objective of that NTSSP problem. So that's kind of how it's done. But as I mentioned, one of the major problems here is that in your first state mitigation analysis, there's a lot of uncertainty as to what type of flooding event is going to happen. And in this case, we had about 800 scenarios of flooding. So the question is that for each mitigation strategy, we need to be able to run, what are the potential recoveries after each type of the scenario floods that could happen. We conducted that. We used basically high performance, a message passing interface within a high performance computing system, which basically all the possible scenarios would be given, and then it would be broken down to different, all the mitigation scenarios would be given to the system, and then it would be broken down for each flood scenario, and then it would be running for the whole time to capture that evolution, and then passing it back to the nodes so that it could make a decision as to which strategy is to be used. So with that discussion on how the modeling and how this computational framework and the optimization framework works, let's take a look at some of the results. First, we have no ex-ante or pre-event or mitigation investment. So let's say we are going with the system as is, not changing anything before the event. So we are starting at about system functionality, and this system functionality here is representative equal to the bridge performance. But as I mentioned again, one can select different system functionalities. But here, the results I'm showing are based on bridge performance. It's going to be constant, no change to it. And then extreme event happens, and there can be a drop in its capacity, either between 40 to 58%. The idea is to get to 63% at the least. And what the program comes in is an expected recovery cost at the second stage of 392.9, which 36.8 of it is direct costs associated with repairing those structures, and then the rest of it is indirect costs. Now, here, I'm showing different investment scenarios in terms of mitigation again, 15, 25, 35, and 45. I'm also showing which bridges the program selected to have accelerated construction versus conventional construction. In each one of them, one of the things that you can see is that the number of the bridges that were selected for accelerated construction technique for the repair process increases with the investment, which is an expected approach because investment is increasing, so it's reducing the time and impact on the network. So it's actually a good approach to take. So here, with a $15 million, for example, investment, as a constraint, what I can say is the program is not using the whole $15 million. It's only using about $12 million of it for the investment. So that's the best result that it's getting from it. You can see the capacity of the system is being enhanced as it is moving towards the mitigation. And then extreme event happens. Obviously, the functionality of the system decreases, but not as much as no investment. So the mitigation works. And then obviously recovery happens. The expected value of this recovery cost is about 200. So huge decrement compared to when you have no mitigation. And that's about 29.5 is direct costs and 179 about for indirect costs. It also showing which bridge identification numbers, which bridges are being fixed or mitigated with which construction technique, and also which bridges in the recovery side are going to be recovered and with which construction technique. So kind of gives that information to the decision maker as well. Here, let's just take a look into, in a sense, again, as I was mentioning, hopefully this works. It didn't work, so let's go back. The time evolution of these changes, you can see different links and breaches here are going to be fixed. And then the flooding happens, and again, the recovery is taking place, and different bridges are going to be fixed again, and that's kind of the system evolution as it is happening. If one takes a look at the kind of the costs, if one looks into the direct costs, again, we said we have different scenarios of investment for pre-event mitigation. Again, not all of that is being used because probably it's not resulting in the best solution. So whatever that we give, the program uses as much as it wants for the mitigation. And what we can see is that the enhancing or investing in the direct costs at the investment or pre-event mitigation results in decreasing the direct costs associated with the recovery. Again, very expected. Indirect costs, you see the similar trend. And then when you look into the total cost, you can see that after some time, really there's not much difference for this specific system as to how much one invests on, because 25 million to 35 to 45, there's not much total cost save. And actually the delta costs are showing here. So in fact, $25 million investment for this specific segments of the road with these scenarios is a very good investment to improve the resilience of the system, in a sense, in face of floods. So with that, I would like to conclude this part. What I've done, obviously, is a simulation tool that captures not only system level vulnerabilities to a suite of different hazards, but also the evolution after hazard happens. It captures both pre-event and post-event kind of decisions and the impact that they have, and kind of the play that they have across the decision making. And we use capabilities of high performance computing. One of the aspects here was that we developed it in such a way that it has modularized codes. It's very easy to be used by practicing engineers or decision makers as well. And again, it's general enough that can be implemented in different contexts for a multi-hazard resilience optimization tool. There's some opportunities obviously here that one can consider looking into, portfolio of assets, considering co-location and resource sharing when the optimization is happening. That provides a more realistic restoration function. Integrating kind of situational awareness through citizen science and social media information and such to enhance kind of that recovery and expedite the recovery process. Uncertainty quantification in different kind of steps of the problem, so that we can kind of characterize and treat that uncertainty. And obviously looking into performance measures that are more connected to community resilience to kind of highlight that aspects of it. These are some of the aspects that are kind of currently we're working as part of our future upcoming work. We have also in our research group looked into transportation infrastructure from other perspectives under other hazards. Specifically looking into that vulnerability assessment component, developing multi-hazard fragility functions, either under scar and earthquake, microburst and earthquake. And the idea is that some of these hazards are codependent, some of them are interdependent, independent, and as such, that needs to be accounted for shock and aftershock deterioration and earthquake and so on and so forth. That's some of the work that we have done previously. We have also looked into a similar system conducting the risk assessment under earthquake events, seismic events in Los Angeles and Orange counties. That's some of the work that has been done. And also looking into this in the context of hurricane and storm surge. And actually we developed the manual of, in the ASC manual of practice, an approach that is a very straightforward approach for kind of understanding the level of the resilience in the system in a kind of fast-paced approach. With that, I would like to thank all of you, the audience, and also acknowledge the funding from all these funding agencies that has supported our work in this area, specifically thanking also my graduate students and undergraduate students that have helped with development of this work. And with that, I'm opening the floor for any questions. Thank you very much for your attention.
Thank you very much, Alice, for this very comprehensive presentation. It also gives me the opportunity to remind everyone the fact that Eurostruct came from a cost action TU 1406, which was quite heavily focused on the derivation of these performance indicators or key performance indicators as a means to standardization, which was the let's say the aspect of that action that was carried through also to the Eurostruct Association. I think you touched upon that topic quite a number of times in this presentation. I would like, though, maybe to ask you or initiate from a question on that point. And many of these indicators are perhaps not easy to quantify, and they come from maybe databases, as you mentioned at one point. They might come from assessments that have some level of bias because they are based on perception or inspection of individual experts. Others might come from quite refined evaluation methods. Is there a way to optimally combine these indicators, as you show, for example, in the spider diagrams? There again, we can have information that comes from various sources and might reflect different qualities. How can one harmonize all of this information into key performance indicators?
That's a very good question. In terms of the kind of those radial charts that we have developed, they're actually coming from all from the same source. But I would agree with the fact that there are different methods to kind of even computationally measure different performance indicators. And there's some level of, I would say uncertainty associated with that, how that modeling is happening, or if one uses actual data, how that needs to be accounted for. And obviously there's some ways, approaches or methodologies to kind of account for that uncertainty associated with that. In the case of our case, however, we used indicators that were coming all from the same model. In a sense, I would say, if there was some level of error associated with any of them, it was equal across, in a sense, all of them. So for the comparison purposes, which was the purpose of those radial charts, it would serve the purpose. But if we wanted to make absolute kind of comparisons between this case and a completely different case from somewhere else, then one needed to definitely account for some of the parameters that you mentioned, and that would make the problem very complex.
Maybe before I transfer or ask Irina to chip in, I wanted to ask or remind the audience to pose their questions always through the chat, and we will then transfer them to the speaker. So Irina, I don't know if you have a question.
I have a question, yeah. So I have one question from the audience. The question is if you have already considered to enlarge your analysis to include also other criteria for the optimization, more related to social and indirect economic consequences of transport network disruption.
That's a very good question. Yes, we have had optimization, other parts of this study that have looked into system functionality measures that are associated, for example, with indirect costs, and that indirect cost in itself has travels delay and also opportunity losses, so for this specific presentation, I tried to focus this a little bit on the bridge side and the structure side, but in a network context. But yes, that it is possible because that's an output of our computational framework, that risk assessment computational framework, and can be used as the measure for the optimization. As for community resilience measures, as I mentioned, one study that we are currently conducting, a major aspect is really accessibility after an extreme event, and that evolution that happens in accessibility. One can also consider the demographics of the community. That's something that we are currently working on. And that would be, again, a performance measure outcome of the risk assessment computational module, which again, combined with the recovery models, one can capture its evolution over time. And then our idea here is to be able to kind of do, for the sake of decision makers, some sort of a, I would say, color-coded map of, which demographics would have less accessibility and how to improve that in a sense, and kind of changing the constraints of the optimization. But yes, it is possible to be done by this computational model.
And just quickly to continue, the indirect consequences which you shown here are linked to the traffic disruption related to the bridge.
Exactly. So these are related to traffic delay. Indirect cost combines traffic delay costs and also opportunity losses. The idea is that because of the either elongated traffic time or because of the loss of connection to other parts of the network, what we call isolation, some trips will be lost, and there's some cost associated or some opportunities associated with those trips that are lost that needs to be accounted for, and that's included in the indirect cost that we have calculated.
Eleni, your turn.
Yes, maybe to stay on the topic of optimization, there is one more question, which I guess is, well, I think is more on the methodological side, but nonetheless probably is an issue for many who attempt to do this kind of optimization or use this optimization scheme. So this is from Huang Bing Liang. He would like, or she would like to know to ask how to obtain the optimum, since when using heuristic methods, we really can only generate a near optimal solution. And I guess this is the case, but then I suppose the real question is how to ensure that we have a solution that we can trust when using heuristics.
That's a very good question. That's the problem with heuristic methods, reality is that simply for a problem like this, it would be very hard to come up with like the absolute optimal problem for the exact reasons that I mentioned throughout the presentation. There are different ways we have tried to address this with having different generations and different sizes of optimization space, all of that, and then kind of doing some sort of a sensitivity analysis, I would say, that would provide an ideal of, whether these are close enough to optimal solutions or not. But I can agree that potentially if one changes the parameters or runs it for a much longer time, for much more generations, they may find other more optimal solutions. The question here would be, how much more optimal it would be, and would it be worth the cost, the time and computational costs. So that's really what it comes down to in a heuristic optimization.
Maybe on that note, I can also ask the following. So for many of these optimization methods, we're discussing usually deterministic means to optimization, but a lot of the aspects you have mentioned, of course, come with uncertainties. So in this case, would it be possible to, or have you experimented with frameworks that take this into account? I guess a Bayesian framework would be a popular choice, but there exist also other alternatives that somehow try to take into consideration this uncertainty involved in these indicators or in these sources of information.
In this specific study, we didn't necessarily use Bayesian methods, but in other work that we had a smaller network, what I call an educational network, we have used that, and it was had a positive impact. In this network, simply it would be hard with any other method to come to that optimal. One other approach we're considering is really database methods, but we haven't completed our studies to see whether they're like computationally positive in that sense. Yes, exactly.
Irina, I give it over to you again.
Thanks. So we have a question from Matthias Pantelli. about so did you apply these decision-making tools in a real-world application? Or actually, yeah, my question would be, did you in some way validate the consequences and resilience predictions? And how would these models could be combined or integrated with the traditional cost-benefit analysis?
Obviously this is implemented in a real life network. That's what we're proud of in a sense. In terms of having the data to kind of compare or validate these, it's very hard. I doubt anyone has that type of data in the field for such a big network. Our approach was really to validate and verify different parts of the computational model. And as soon as we were fine with it, we would move on to combining them. So that's really the way that we have gone about validating these results. And again, as I mentioned, this is something that is going to be implemented by a real estate agency. So that's really how close it can get into being implemented. As for cost-benefit analysis, yes, we actually have another part of this study that looks into a smaller segment of the network and conducts cost-benefit analysis. And the reason for looking into a smaller network was just because of the type of detailed data that was needed. And for that, we, in a sense, dissected a portion of this network and looked into a specific set of assets that was actually presented to us as a set of assets that were being flooded over and over on an annual basis. And to conduct benefit cost analysis in terms of exactly mitigation studies as to whether it's worth to spend so many $1 million in kind of raising the road segment or bridge segment to prevent overtopping or also damages. And yeah, we have used that in that context as well.
Maybe on the topic of, this information or the outcome of these methods used in a practical sense from, I don't know, real estate agencies, or in other cases from roadway owners and agencies, is there a special care one needs to take in the way in which this information is translated into a usable outcome? Is this a consideration you have to make, or is it, is it easy to speak of let's say, risk in pure quantitative terms, or does it need some further work to make this easily translatable for use or adoption in practice?
Definitely on the side of adoption by state agencies, there needs to be a lot of communication happening and probably education in the process. What we are planning to do, the state has something called a project prioritization. This is a long-term planning tool that accounts for different perspectives, mobility, safety, and so on and so forth. And our idea is that we create, boil down all these analyses into what we call a resilience index. And that index would be something that weighs those values or those numbers that are being generated by the tool and becomes another decision parameter. As to whether a state agency will necessarily follow that or not, it's really a multitude of decisions that goes into it, but that's an extra piece of information that is provided and can be used as a measure for decision making.
Mm-hmm.
I have another question from the audience. So the question is, as you said, Alice, also that the infrastructure systems there will be always failures, but although the mitigation measures are implemented. So how should the resilience target be set? And how much loss of functionality are we able or willing to accept In other words, how much to invest in resilience?
It really comes down to a community and a stakeholder and asset owners kind of thresholds, I would say. It's as correctly mentioned, you correctly mentioned, we do not have necessarily the resources or the knowledge to 100% go and mitigate everything. So failures are going to happen. It's a part of actual in a sense, that's kind of what highlights importance of thinking from the perspective of resilience. It's not about hardening everything in such a way that nothing fails. It's about knowing what will fail and being prepared for that and having the best strategies to recover from it. And that's really what it comes down to. So yes, mitigation is very important, but mitigation is really a portion of resilience. From a resilience perspective, a very prepared community would be one that understand what can fail, has plans for it to be, in a sense, recovered or repaired into a state that it wouldn't be any more vulnerable to future events of such size or such intensity. So all of that is a definition of resilience. And so the idea is that, and the whole reason this framework we have developed is kind of focus on the two stages and their interrelationship is really to be able to capture that full spectrum of resilience, which is not only pre-event, but also during the event and also after the event, and how long it takes to recover.
Alice, maybe one more question from the audience, which is on essentially the aspect of cascading effects and how this is taken into account. So this is again a question from Huang Bingliang on whether the recovery simulation for the transportation system considers the interdependencies, so the cascading effect with other infrastructure networks or components, for example, communication systems, electric power systems, and how? So.
Well, this is a very good question, and the clear response would be in this program that we have developed, no, it doesn't have interdependency. I would say the only effects that are considered are the first order effects because of damage to road or bridge segments, to the transportation network itself and its users. So that's really first order effect in the consideration of resiliency. But that's right, these factors are important and would impact how fast the recovery could happen or could take place. Things such as how long it takes for debris to be cleaned up before access is granted to different parts, whether resources are available, whether crew are available, whether a material is available, whether the contracting process is available. All of that has an impact on how fast one can recover, in addition to obviously that interdependency that was mentioned, who gets to fix what first in that context is an important thing. And there's some, we know that there's some aspects of, in a sense, competing interests there as well. None of that was modeled in here, and it was just impossible for a huge network like this that we are modeling to consider those aspects. But one can definitely look into smaller networks and kind of try to capture those effects as well.
Thank you.
Yeah, so just so for instance, we have done similar study, but indeed in a much smaller area. So do you take into account flood protection system, like, I mean, whatever embankments, levees, and what kind of failures did you take into account?
That's a very good question. In this specific study, we are assuming that the flooding level is whatever it is. What you're mentioning is would be some sort of a decision output from this to decrease the exposure to the system, which would require some sort of dynamic hydrologic analysis on the flooding scenarios and flooding hazards. And we didn't have that capacity at the time. However, that's something that is being conducted now with some hydrologic models that are dynamic and then capture the potential implementation of, in a sense, exposure reducing measures such as flood walls, levees, and also catch basins and such. Yes, yeah. Not included in this study though.
Thank you.
Alice, I think with this, we're reaching near the end of the seminar. And as always, I want to ask you to maybe leave us your message on what you would like the audience to take from this talk and this discussion. So what would be, let's say, your closing message?
Well, I wish I could have prepared something for that. So I think any type of study that claims to be being kind of directing in towards resilience, especially with the infrastructure, needs to be conducted in coordination with real life stakeholders. When we talk with the stakeholders and asset owners as to what is keeping them awake at night in a sense, and what are the aspects that they want to kind of be considered. Sometimes it's very different from the assumptions that we are making in the academia. And for these models and frameworks to be useful, really the best stages to, the best approach is to kind of involve them early on in the communication so that what is produced is useful. And I can say that we have to a large extent done that in this study, and as such we can see it to be implemented.
Great. So let me also remind everyone that if you would like to visit, you can visit our webpage to catch a recording of this talk if you would like to see again some of the concepts presented or of previous, or the talks of previous speakers or previous live talks as well. Sergio, our administrative assistant, has placed the link in the chat for your convenience. So we invite you to log in and also check the page for our upcoming events. There will be 2 more live talks that are coming up in the next months, so you will find more information then. I want to thank Irina for co-moderating this talk, and most of all also Alice, of course, for being here today and sharing with us her exciting research, which I think will inspire many. And of course, everyone for joining in, and hope to see everyone soon. Thank you.
Thank you very much.
Thank you very much, Alice.